Hey guys, so today we are going to be starting Unit 8, Chapter 12, which is all about a chi-square goodness of fit test. And so today our learning targets are to state the appropriate hypotheses and compute the expected counts in chi-square test statistic for a chi-square test for goodness of fit. State and check the random 10% in large counts condition for performing a chi-square test for goodness of fit, and calculate the degrees of freedom and p-value for a chi-square test for goodness of fit. So if you notice a lot of words that we're kind of familiar with, so some of the conditions and hypotheses, so a lot of stuff that we've been doing, now we are just doing a different form of significance test though. And so for our context for today, we are going to be studying which color M&M is the most common. So the company that makes milk chocolate M&Ms claims the following distribution: 13% brown, 14% yellow, 20% orange, 16% green, 24% blue, and 13% red. But is that true? Well, last night I ate a whole bunch of M&Ms and I recorded down all of the different, how many of each color I got. So I had 55 brown, 92 yellow, 101 orange, 73 green, 74 blue, and 66 red for a total of 461 M&Ms. So if we wanted to test this was true, just like we've tested claims before, it was always handy to collect our own samples. So that's what I've done in problem 1. I've created my own sample that I'm going to test against the claim. And so in order to do this, I need to write a hypothesis. And so the hypotheses, the null hypothesis, remember we always go based on a claim that's being made and assuming that that claim is true. Well, the claim comes from the context of our problem. We're talking about the claim of the company and the distribution that they think is true for M&Ms. And so we're actually going to write this hypothesis a little bit differently than we've been doing before. We are not going to write it symbolically. So when we were doing hypotheses, we would say mu is this or p is that. But the problem is now we aren't just testing one thing. We are testing proportions for multiple things, right? It's the proportion of brown and yellow and orange and green and blue and red. So it's kind of like we have these different categories and we are testing a claim for a proportion for each one individually. So I would have to write down the P for brown M&Ms is 0.13. But then the probability or proportion for yellow M&Ms is 0.14. And the proportion for orange M&Ms is 0.2. And so on and so on. And rather than do all that, it's okay to actually just write your hypotheses in words now. So we have from the company a claimed distribution. That we are testing to see if it's true. So our null hypothesis is simply going to be that the claimed distribution of M&M color, so there's some context too, is true. So we have our claim distribution. We're saying that we're going to assume that it is true. And for the alternative, we are trying to prove that the claimed distribution of M&M color is not true. All right, so we have our hypotheses. What do we do next? So it says, let's suppose that M&M's claimed distribution is correct, assuming the null is true. If they are correct, how many of each color would you expect to get in our sample? So I collected a sample of 461 M&Ms. If M&M's claim was true, how many brown would you expect to get? Yellow, orange. Pause the video now and see if you can come up with the expected values for each color of M&M. All right, so I'm going to fill these in here. Hopefully you at least gave it some effort. But for brown M&M, I got 59.93. For yellow, I got 64.54. Orange, 92.2. Yellow, 73.76. Blue, 110.64. And red, 59.93. So all of these are the expected values for each category for a sample size of 461, the sample size that I had used, right? So essentially, how did I find this if you weren't able to do it? For brown, I just did the expected or the claimed proportion of 13%, so 0.13, times the total number of M&Ms, my sample size, 461. And so taking 13% of 461, I would expect to have 59.93 brown M&Ms. And now, even though it doesn't make sense to have a decimal of M&Ms, for expected values, we are not going to round. We always are going to keep that decimal because that's what gives us our accurate test statistic in the end. So what did I actually just do here, right? I did the proportion for brown M&Ms, 0.13, times our sample size of N. So really I'm doing N times P. And maybe that looks familiar to you. Remember the large counts condition? So when we are doing expected values, we're really testing kind of the large counts condition. I'm going to actually add, so notice we did it for all categories: brown, yellow, orange, green, blue, red. So I'm going to say N times P sub I. And I just represents the fact that we have multiple different P values that we're testing, one for each category. All right, so now that I have my expected values, you could use that to fill in this table and work through to calculate your test statistic. So we're going to go with the observed values from before, expected values that we just found, fill in the table, and then you're going to subtract them, square that, divide it by the expected, and I would like you to get all the way down here where you're going to add up all of the numbers in this last column to get our test statistic. So pause the video now and go ahead and calculate that. And then also do your best to answer 4 and 5 based on what we know about test statistics and how we think the chi-square test statistic might work. All right, pause the video now and give it a shot. All right, so hopefully you took some time to pause. And I'm going to come down here to my chart all filled in. I've got the observed values from above, expected, and then I worked through it. I subtracted observed minus expected, squared it, divided by the expected values, and I ended up finding the final test statistic as 25.69. So this is our test statistic, which before we know we found Z as our test statistic, we've found T as our test statistic, but now the test statistic for this type of test is called chi-squared. And the symbol for chi-squared looks like a squiggly X squared. And so chi-squared is equal to the summation. So this means the sum of, oops, sorry guys. It is equal to the sum of the observed values minus the expected squared over the expected values for every single category. So basically, it's exactly what you just worked through and found by doing observed minus expected, squaring it, dividing it, and adding them all up. So we're not going to take this problem much further, but what if we were going to? What if I asked you to find a p-value for this test statistic? Remember, the p-value is that probability of our observed results happening if the claim was true. And we typically, before, when we had a z-score, we would find our p-value from table A. Or with a t-score, we would find our our p-value from table B. And so with a chi-squared, we are going to find our p-value from, you might have guessed it, table C. So table C is the other side of our t-table. Maybe you've seen it. It looks like this. And this is the chi-squared critical values and p-values for these types of problems. Now, as you look at this, notice that for chi-squared, we do need to know a degrees of freedom. And degrees of freedom actually works differently for chi-squared than it did for t. And so to find the degrees of freedom, we're actually going to look back up to just these expected values here. In order to find expected values, our degrees of freedom, we are going to do the number of categories minus 1. So for this one, we have brown, yellow, orange, green, blue, red. So we have 6 different categories. And so 6 minus 1. So we have a degrees of freedom of 5 here. So we would use degrees of freedom equals 5. We would use our table Z, and we would find a chi-squared p-value that was less than 0.0005. Now, we'll go more in depth with this tomorrow. We'll look at the calculator too, because the calculator can do this for us as well, and we love using our calculator. So we will get to that, but just right now, let's kind of go over 4 and 5 and what you thought you might expect for test statistics. So for 4, what value did you expect that you would get for a test statistic if our sample was very close to what is expected? So if our sample of observed values was very close to the expected values, then we would assume that we could get a value for the test statistic that was close to 0, because when we do observed minus expected, those numbers will be close to 0. So when I subtract the observed minus expected, if they're very close to each other, then they have a very small difference. And so therefore, it would give us a really small test statistic. Whereas in question 5, what would we get for the test statistic if our sample was very far from what is expected? Well, we would expect a very large number then, because if they're very far off, then they'll have a very big difference here in this column when I subtract them. And as I square it and divide it, it should just be a much larger test statistic than if they were close together. All right, so hopefully this was a good introduction so far to chi-squared tests. Let's go ahead and write a few important ideas before we move on to the check your understanding. So my first important idea is going to be about the hypotheses for this type of test. So we have our null hypothesis, and the null hypothesis is the claimed distribution and with context is true. And our alternative then is that the claimed distribution with context is not true. And so remember that we also now are finding expected counts or expected values. And that is very similar to the large counts condition. It's n times p for each different category of our distribution. All right, for our next important idea, this one is about the test statistic. And this is our chi-squared value. So it's kind of that curly, well, that's a little too curly. X squared, that's chi-squared. And it is the summation of the observed value minus the expected squared divided by the expected. So you do that for all of them, and you will sum them together. Most likely you will use your calculator to do that instead. And then let's make a note about what we just finished talking about, a larger chi-squared. Well, we didn't finish talking about this, but we talked about smaller versus larger chi-squareds. And so the larger chi-squared, if you remember, we said that we thought it would be larger if our sample was far away from expected. And remember, this is typically when we would choose to reject the null, because our observed sample is so unlikely, if the claim was true, that we say that we don't believe that the claim is true. So a larger chi-squared, that means that we have more convincing evidence for the alternative, for HA. All right, and our last part of this important idea here is all about the degrees of freedom and p-value. So remember that your degrees of freedom, it is equal to the number of categories. I'm just going to call that K. That's typically what it's what variable we use here, minus 1. And so we'll make that note. K is the number of categories. And then we take our p-value and we go to table C. But you can also use your calculator. And so we will learn the calculator method soon. All right, so why don't you go ahead and stop the video, do the check your understanding, and we can check this tomorrow together. Tomorrow we're going to move on to actually doing state, plan, do, conclude with chi-square goodness of fit tests.